Hello everyone, I'm Haoxin and in this video I will present our tool FastKLEE, a faster symbolic execution engine where reducing redundant bound checking of type-safe pointers. The presentation will be divided into the following parts. Firstly, I'd like to give some background about symbolic execution and type inference. Secondly, I will open the problem and propose our solution to elevate it. Lastly, I will show how end users use the tool and then conclude this work. Let's go through the background first. How does SE work? Note that the SE here refers to symbolic execution in this presentation. Given a test program, SE feeds symbolic inputs into the program and encodes execution paths to path constraints. Then, by solving the path constraints under the constraint solver, SE gives out concrete inputs that examine the same paths that are explored before. As shown in this picture, a popular flavor of SE is interpreting-based SE, which interprets IR to simulate running a program. A majority of SE engines follow this design, such as well-known CLEE, Anger, and S2E. Type inference is a technique used to detect the type of expression in a programming language. Typically, in the C program, it was used to help inference C pointers to be type safe. A notable type inference system that aims to guarantee memory safety for C is called CCQ, which shows that a large portion of pointers can be statically verified to be type safe, and only a small portion need runtime check. As shown in the simplified workflow, CCQ leverages an inference algorithm to classify pointer types into three main categories: safe, SEQ, and wild. Among them, safe and SEQ can be statically verified to be type safe, and only wild pointers need at the runtime check. Okay, now we have known some preliminaries about this work. Let's turn to see what problem this tool focuses on. As we mentioned before, the majority of SE engines are based on interpreting IR. As also pointed out by existing studies, such a design is easier for implementation, but it scarifies the performance. Therefore, how to accelerate interpreting-based SE engine is a challenging problem. To investigate the problem, two major types of studies are devoted to speeding up those engines. The first one is compiler optimization-based approaches. They either select existing compiler optimization or design customized optimization for faster SE. The second one is focused on reducing the path exploration and speeding up the constraint solving for faster SE. Although these approaches have shown to be effective, they did not consider that interpreting alone can have performance downsides. More specifically, their engine treats all pointers equally and performs bound checking for all of them. In summary, the remained performance issue and limitations in existing SE engines motivate us to design a new solution to mitigate the problem. Therefore, we propose a tool FastKLEE in this study. There are two key insights behind our tool. First, the number of interpreted instructions tend to be huge. It's usually several billions only in 1 hour's run. Secondly, a large portion of pointers in C can be statically verified to be type safe, as we mentioned, and reducing the overhead of redundant bound checking of the most frequently interpreted ones could accelerate the execution. Specifically, FastKLEE first used a type inference system to classify point types and produce a checklist for unsafe pointers. Then, it conducts a customized memory operation to check bound only for those pointers in the checklist. Now, let's move to the tool demonstration part. The basic usage follows the design of the tool. The initial step is to install the tool. Users can use Git tool to clone the source code of FastKLEE and then go to the folder, execute uh, setup.sh to build the whole testing environment. Now I will use the example here to illustrate the usability of FastKLEE. The cat.bc is the target program we are going to analysis, and there are three tiny scripts that we are going to use to perform different tasks in FastKLEE. The first is to instrument the IR code for preparing type inference, which use the LVM link to link two BC files into one. And then in the type inference process, it will use OPT to load the CCQt library to perform the analysis. Due to the analysis process, a text file which records the all unsafe pointers will be stored. Here will be stored into the checklist, which will also be used in the later faster symbol execution. And then the final step is to conduct the FastKLEE. Those commands can be changed by users for their different purpose. And now we conduct the symbol execution. Okay, now the cat is under analysis with FastKLEE. Okay, please allow me to conclude this video now. I first introduce some background about this work and then describe the problem this work focuses on. Next, I presented the proposed solution, FastKLEE, to elevate the problem. Finally, I showed how users could use the tool to perform faster symbol execution. Here is the reference used in the presentation. Okay, thank you for your watching, and please feel free to contact me if you have any ideas about this tool. Thank you so much again.